or you will see it soon, that says we're going to meet in the electronics lab like we did last week tomorrow. I will spend half the time kind of continuing talking about the mathematics stuff that we've been doing. And then the second hour we will just use to work on MATLAB. And that's the last time we're going to meet as a class to work on this MATLAB assignment, which will be due sometime mid next week. So you really want to make sure that if you don't have a working algorithm that's doing those integrated solutions to the differential equation, and something that's stepping through the energies and have a good way to determine when you've passed an energy eigenvalue, that should be our highest priority. If you do have a working piece of code, then certainly use tomorrow's time to make the output of your code look nice, because that's also a challenge, but that's a secondary challenge in MATLAB. The first thing we want to do is just make sure that we get the harmonic oscillator case where we know what the solution should look like, we know what the energy should be, make sure that they're working. Okay, we were talking about some mathematics that you're familiar with, but we're extending it into a realm that you're probably not familiar in using these terms. So we've been talking about a vector space, which sounds familiar enough to all of us. And we gave the axioms. Why am I not able to? Let's try this again. Point with this. There we go. The axioms for vector space, which are all pretty much things you wouldn't, it's hard to imagine calling something a vector space without all of these things down at the bottom working, and you'll just assume that they're true without even thinking about them. But the one we were concentrating on last time was closure. It's possible to describe a collection of things that you want to think of as a vector space, but then you might realize that when you add two of them together, it's not the same kind of thing. And so it isn't closed, and so you shouldn't be calling it a vector space. Same thing with scalar multiplication. If you multiply by 1/2, then if it isn't in the same collection, you shouldn't be calling that collection a vector space. And we ended talking about inner products. So mathematicians, when they define an inner product, it has to satisfy these axioms. And here, I guess we were starting to think about conjugate symmetry here, and that's something that we don't normally think of for real vector spaces, right? When we're thinking in 3 dimensions, that is a vector space over the real numbers. In other words, your scalars that you scalar multiply by vectors in 3 dimensions back in physics 210 are real scalars. And the inner product that's defined between 2 vectors is always a real number. And so taking the complex conjugate of it in this case has no effect, which means that for a real vector space, it doesn't matter whether you take v.w or w.v, right? The inner product means the same thing as the dot product. So we don't really worry about the order we put them in. But when we have complex vector spaces, and that's what we're talking about in quantum mechanics, those constants or scalars that you put in front of vectors to scalar multiply can generally be complex numbers. Then the inner product might be a complex number, and we don't want it to be the same either way. We actually want it to be the complex conjugate when you take the inner product in the opposite order. And so we ended with this voting question, and I just told you that the answer is B. Normally if I have a vector with components, A1 and A2, maybe those are, or AX and AY, if you want to think of X and Y components, and another one with X and Y components, BX and BY. We would want to say, so this is the components of A, this is the components of B. We would want to say, or our good old familiar definition of the dot product, which is like the inner product, we say is AX BX plus AY BY. And that's not going to work when we have complex vector spaces. It has problems. And let's see what the problems are. Why is B going to be the generalization? Now, B reduces to this formula, of course, when we're talking about a real vector space, but we need those complex conjugates, the stars on the first vector in the inner product. So let's imagine that, so here we're thinking of a two-dimensional vector space, so which we're going to represent the vector by its two components, and those components we're going to imagine are complex numbers. They're not real numbers. So, I could think of the most general complex number is a plus bi, where a and b are real numbers, right? Any complex number can be written in that form. So let's imagine its first component is a plus bi, its second component is c plus di, where the a through d are all real numbers. And that's the most general case of what the components of V could be. And let's just calculate using this first definition, which is kind of the one we're familiar with, right? That's the way we normally calculate dot products. When we do that and take the inner product of this vector with itself, according to this definition, we're told we need to square a plus bi and square c plus di and then add them together. And you'll see that there is an imaginary part that doesn't disappear from this, right? There's a cross term here, which is 2abi, and there's a cross term from this one, 2cdi. And so in general, those things, those parts of the inner product that have eyes with them are not going to disappear. So this is not real in general, and that violates one of our other axioms of an inner product, is that the inner product has to be a real number, in fact, a non-negative real number. Can't be complex, so there can't be any eyes in it, right? Inner product is always going to be real. So how is that solved by this second one that we're saying is the correct answer that we're going to use? Well, in that case, we're told that we need to multiply a plus bi times a minus bi if we're taking the inner product of a vector with itself. And same thing for the c plus di times c minus di. And in that case, all the cross terms cancel. The outer cancels with the inner in this case and in this case. So all the i's go away. And it reduces down to a squared plus b squared plus c squared plus d squared, where all those are squares of real numbers. And that agrees with the fact that it's got to be a non-negative real number, right? If a, b, c, and d are all real numbers, their squares are non-negative. So when we add them together, they're certainly greater than 0 real numbers. And it also shows that we're only going to have this inner product of a vector with itself equal to 0 if the vector is the 0 vector. Going back here, right? Suppose that this output is 0. Well, the only way, if a, b, c, and d are real numbers, the only way that this side could be 0 is if a is 0 and b is 0 and c is 0 and d is 0. And what that means is the first component of V is 0, the second component of V is 0. That means it's the 0 vector. And that's what that last axiom is saying, that the inner product of a vector with itself is only 0 when the vector itself is the 0 vector. Okay, so that's just a little bit of a side note on the inner product axioms and why we've got that weird star, at least in the case of finite dimensional vector space. Oh no, my symbols didn't work here. So this is supposed to be that boldface font R for the real numbers over the real numbers or over the complex numbers. That's what those two symbols are supposed to look like there that you see in math classes. Okay, so a vector space is a collection of things closed under finite linear combinations. That means if you have a vector space, you should be able to take any linear combination of them and you get another vector in your space. It's closed, okay? And our big examples that we sort of listed last time that we're going to use in quantum mechanics for vector spaces are the set of square integrable functions on the real number line. Okay, we call that capital L2. The set of square summable sequences. And when we say square summable, we mean magnitude squared. So you have a sequence, C1, C2, C3, C4, C5, C6, and we take the magnitude of C1 squared plus the magnitude of C2 squared and so on. Do that infinite series, it should give something completely finite when you calculate that. And notice that, we're really thinking of these as the same vector space, right? This is one way to represent what state we're in, and this is another way to represent what state you're in by giving all those CNs, the collection of all the CNs. So they're the same information. They're just two different representations of the same vector. The third example, which is really a collection of examples that we'll get into when we start talking about spin, is finite dimensional vector spaces, which are just like what you've used before, right? A two-dimensional vector space or a three-dimensional vector space. But in general, ours will be complex vector spaces. So the components will be complex numbers rather than real numbers. Okay, so examples in quantum mechanics of, representations of a state that a particle could be in that correspond to capital L2. Well, suppose my state is supposed to be the state a particle is at time t equals 0. I just sort of labeled this abstract vector as psi with the subscript t equals 0. It's supposed to say, this is the vector that represents the state of the particle at time t equals 0. If I wanted to represent that in capital L2, I would, one way to do that is to give a function of x at time t equals 0. That's the way we've been doing it. So we're saying this is just one way to represent this abstract vector. There are other ways, right? I could do the CNs or whatever, but this is one way to represent it. If I got an abstract vector f, generally, if I'm labeling it as a function of x, f here as a function of x, whatever that function's name is, I tend to kind of use that as the label for the abstract vector over there. Though there's no rule about that. You just have to kind of use something that reminds you of what that vector means. So if there's this association, this is the way we're going to represent the state, and this is the abstract vector. Why not use an F there? Similarly, if we have a solution to the time-independent Schrodinger equation, that's one way to represent an abstract vector, and why not label it by psi n? There's no rule that says I have to do that, but everyone would kind of know what we're talking about, right? That is the abstract vector that represents a state of definite energy, for example. Okay, what about capital L2? Well, we just said I could write this as a linear combination of the psi n's, and the coefficients would be the CNs, and the CNs would be completely equivalent as a representation. And therefore, another way to represent this state as an element of little L2, the square summable sequences, is by giving an infinite collection of CNs. You tell me what those coefficients are, and you've told me what the state is. So that's another way to represent it. Same state, different representation. Okay. And similarly, usually when we're talking about finite dimensional vector spaces, often we'll write them as column vectors, right? You're used to doing that, at least if you're in linear algebra, but sometimes in physics too. So here is if this is a vector in a two-dimensional complex vector space, then I might have one complex number here, another one there, and I put them in a column vector, displaying what the components are. It's fairly common. In fact, I could do the same thing with these representations up here. I might think, there's no reason I have to just think of these as an abstract set. I could line them up in a column vector, except instead of just having two components or three components in my column vector, here I have an infinite number of components. So I'm going to think of this as sort of like a vector space where vectors have an infinite number of components. And similarly, I might make a column vector out of f of x, and you can think of the value, instead of having discrete locations for the value like I do in this column vector over here, we have a continuum of locations for value. And so as x changes along the column vector position, the value that we're placing in that location changes as we go down. So there's like a continuum. It's hard to draw that there, but it's like a function as you go down, a continuous function. Okay, so intuitively, we hopefully you have the idea that an inner product is sort of in very loose terminology, the degree of overlap between two vectors, right? And in particular, if their inner product is 0, we say they're orthogonal. They don't overlap at all. In other words, one's projection onto the other one is 0 projection if they're orthogonal. Okay. Again, I'm following through that page of notes that's printed kind of sideways and using some examples just taken from that scan. So the inner product. So let's imagine I'm saying I've got two vectors. I'm going to call them f and g, and they're represented in that position representation by functions f of x and g of x. How are we going to define the inner product? Well, we already talked about how to do it before, right? Whichever one is the first one, you put a star on that function, no star on the second one, and then you integrate from minus infinity to infinity. We called that the inner product a few weeks ago, right? On capital L2, similarly, just like we needed that conjugate symmetry, and that required we put a star on the first one when we multiply products of components. So in this case, if I have a vector in represented by some sequence of numbers in little L2 and another vector represented by another sequence of numbers, then the inner product is going to be the sum of the products of the components, each component, but with a star on the first one that appears in the inner product. And likewise on finite dimensional vector spaces, except I only have to sum from 1 to 2 or 1 to 3 or something like that. Okay, please stop me if, I feel like I'm talking fast, but stop me if something doesn't make sense or you want clarification there. We define vectors to be orthogonal, and when it's an infinite dimensional vector space, it's kind of hard to visualize things being perpendicular. We usually think of orthogonal as being same as perpendicular, but even in cases where it's hard to imagine the geometry there, we say they're orthogonal if their inner product is 0. Okay, so that's just what orthogonal means. Let me just make sure. I think there's a worksheet problem I wanted you to do here. Yes, so I think I handed out 2 worksheets last time. One of them only had a front page, and one of them had a front and a back page. It has 9 problems on it. And let's just pause here and do worksheet problem number 2. On the worksheet, I believe that only has one side to it. Yes. So that's the one where you had these, you were circling the yeses and the nos at the top. Let's do problem number 2, which is I'm giving you representations of states as functions of x, and we want to calculate the inner product of those. And then think about if somebody gives you a state, how would I come up with another state that's orthogonal to it? That's what part B is about. And Alvis, these are the worksheets we were working on last time, so they should be under Monday's date.
Oh, here. Worksheet 2, correct?
Oops. All right, let's plug them into this formula. Probably, I should have written out more, more formally. We don't say an abstract vector is equal to a function of x in the same way that people might hesitate to write down this statement, although you do see it all the time. This is an abstract representation, and this is a perfectly definite representation, but it might be different in a different basis, right? These are components in a particular basis, but if I switch my mind about what the basis vectors are, these numbers would change. So this is only one representation. So, maybe it's a little bit more careful to say, I'm going to associate this vector, this particular vector, with this particular representation in a particular basis. Okay. When we do this, the definition is whichever one appears first in the inner product gets a star on its function of x in order to compute this inner product, and the other one doesn't. Okay, so that's the integral from minus infinity to infinity of, this one needs a star. Now the only I there is out in front, so the 4i turns into a minus 4i, right? And then I have an e to the minus 2x times e to the minus x, absolute value of x is e to the minus 3 absolute value of x dx when you combine them into a single exponential function. And then, well, how could I go about analytically completing this? Right, I know, I can bring this constant out in front. The integrand is symmetric with respect to positive x's and negative x's. So it's 2 times the integral from 0 to infinity. And we'll see how that helps us, right? So I have a minus 4i. I'm going to put a 2 times the integral from 0 to infinity of e to the minus 3 absolute value of x dx. But for positive x values, I don't need the absolute values. And then I can just go back to our good old calculus stuff, right? I know how to integrate e to the minus 3x. The antiderivative is e to the minus 3x over minus 3. And so therefore I can write this as e to the minus 3x over minus 3 evaluated between 0 and infinity. At infinity, it goes to 0, so the upper limit goes to 0. At the lower limit, you get an extra minus sign, which cancels that minus sign if I'm doing this correctly. So e to the 0 is 1. So I think this whole thing that I have a bracket underneath there is 1/3, if I'm correct. And so that whole thing then combines together to be minus 8i over 3. Which is, one thing to illustrate is that inner products can certainly be complex numbers. They don't have to be real, right? The inner product of a vector with itself has to be a non-negative real number, but the inner product between two different vectors can be any complex number you like. So nothing wrong with that I sitting out front. Okay, any questions on that one? Just mechanics, making sure you don't get, fooled by all, these little I's sitting out in front and whatnot. B asks for a representation of a vector as a function of x that is going to be orthogonal. That means it has an inner product of 0 with this function. So this is the state f being represented by this function of x. It, it looks familiar. Sine of 3 pi x over 7 or 0 for x between 0 and 7 or everywhere else on the x-axis. I mean, that kind of looks like our infinite square well, one of our energy eigenfunctions, except I didn't bother putting in the normalization factor. And it looks like it corresponds to n equals 3 on a well of width 7, right, between 0 and 7. So that's a hint. So if I want to write down a function g of x that's orthogonal to it? Well, one way to do it is, of course, I could write down a function that's only non-zero where this one is zero. And then certainly the integral is going to be zero, right? Because one function under the integrand or the other one would be zero. But it might be more of a challenge to say, well, okay, how about we say your function can't just be zero in the region between 0 and 7. Let's make it a little bit interesting. But he come up with an example of a function g of x that isn't just 0 between 0 and 7, and yet has a 0 inner product with this function, using our knowledge already from the infinite square well work that we've done. Yeah, sine of pi x over 7, 0. Same cases over there. Or sine of any n pi x that's not equal to 3. It's not equal to 3, and it's a, positive integer, then these two functions are going to be orthogonal. That was one of the things that Griffith shows in the section on the infinite square well, is that different energy eigenstates for a particular potential are always orthogonal to each other, ones that correspond to different energy eigenstates. And that, when we say they're orthogonal, that means their inner product is 0. So you could try, doing this. The claim is that the integral from minus infinity to infinity of f star of x times g of x dx equals 0. We're asking that question. You could have done them in the opposite order too. You can think about it if you switch the or put the star on this one. If one of them is 0, the other one's going to be 0 with the other ordering there, right? Because if you integrate something and get 0, then when you integrate its complex conjugate, you're going to get 0 too. So this reduces down to the integral from 0 to 7 of f is sine 3 pi x over 7 sine pi x over 7 dx. Sorry, I want to make sure it's not an emergency when somebody's calling me during the middle of class. Okay, and the claim is that's 0. You got to think about probably do some product of signs kind of trig thing to, that's how you would do it in elementary calculus. Questions on those? All right, good. Let's keep going with the mathematics. The norm is just a mathematics way for saying the length of a vector or the magnitude of the vector. You're familiar with both of those. The norm means exactly the same thing. How are you going to calculate the length of the vector? And generally, we're going to do it the same way that you do it in elementary, with 3D vectors, which is to say you take the inner product of a vector with itself, right? If I have a vector v that has components vx and vy, maybe it's a vector in a two-dimensional vector space, then if I take the inner product of that vector with itself, I get vx squared plus vy squared. And this says to calculate the norm of a vector, which we use a double kind of absolute value signs to usually indicate. You can put the vector symbol underneath, or you can just put a v there, and then people will know it means the norm of the vector that has that symbol associated with it. To do that, the claim is, well, this isn't the length of the vector. The length of the vector should be this from the Pythagorean theorem. And so we take the square root of the inner product of a vector with itself. So here it is in the new notation, right? Our new notation for the inner product. And I'm just making sure I'm not rushing through. I think I have some examples on here. Okay. So in quantum mechanics, we're always going to, there are other norms you can define if you're in a math, graduate school math class and analysis, you'll define all sorts of different norms. But in quantum mechanics, we're always going to relate the norm of a vector, that means the length of the vector, to the inner product. So if you have an inner product defined, you're just going to take the square root of the inner product of a vector with itself, and that's the norm of the vector. And we say a vector is normalized if it's if the inner product of itself is 1, which means the square root of the inner product of a vector with itself is 1, which means the norm of the vector is 1. Okay, I think there's another one on here that I wanted you to do. Worksheet number 3, same worksheet. What's the norm of the vector e to the minus x squared? Find a normalized version of this vector. Did I give you guys the integrals on this one? It's on the other one, the Gaussian integrals that you might need there. So look on your other worksheet that I handed out. There are some Gaussian integrals at the top. What's the norm of that vector? And what's the norm of another vector down at the bottom? I mean, I guess I should say that all these examples are not, there's nothing subtle about them at all. It is forcing you practice with the definitions and, remembering what we mean by a norm, remembering what orthogonal means and all that kind of stuff. But the calculations are supposed to be easy. I think I see a mistake in my solution here. So I'm just following through the rules here, right? And I guess I should point out again that sometimes we'll want to say the norm of this vector, but boy, I really don't like writing all those brackets and things. So we'll just say the norm of the symbol, and you'll know it means the norm of the vector without putting the vector symbol on there, is defined as the square root of the inner product with itself. We're never going to vary from that in quantum mechanics, but in advanced math classes, there will be other norms that you'll see if you end up taking those classes. So that's the square root, and here's the inner product of this function with itself. I don't need a star because it's a perfectly real number, right? So I just put the function next to itself and integrate from minus infinity to infinity. And then I've got to look up my Gaussian integrals, which are on the other one. Well, let's see. This is 2 times the integral from 0 to infinity, because this is an even function, right? So I'm going to put a 2 out in front. And then I'm going to look at the integral from 0 to infinity of e to the minus ax squared. For us, a is equal to 2. So this is equal to, the integral from 0 to infinity is 1/2 times the square root of pi over 2. That's what's under the square root. So it looks like my 2 cancels the 1/2 that I have there. And therefore, applying the square root that's on the outside, this looks like pi over 2 to the 1/4 power is the norm of that vector. So, I mean, I guess you'd say, hey, we learned it's not normalized, right? That's definitely not 1, whatever it is. Okay, B asks for what's the norm of the vector e to the minus x? What do you say about that one? Maybe I didn't give you enough time, but let's just try to amend this. Now this is e to the minus x here. No square on it. Okay, we're going to calculate using the same thing. The only thing that changes is I get an integral from minus infinity to infinity of e to the minus 2x in the integral. And what do you say about that integral? It's divergent because, wow, it behaves nicely as x goes to plus infinity, but it's diverging as x goes to minus infinity. There's an infinite area under the curve. Of course, it's not an even function, so I can't divide it up to 0 to 2 times the integral from 0 to infinity. So this function, we would say, we would say the integral is a divergent. The function itself is not normalizable because its norm is infinity. We would have to divide by the square, divide by the square root of infinity to normalize it. That's going to make 0. So we lose everything when we do that. So this is divergence, and we would say, well, there's no sensible norm to this function, and that means we're not going to consider it. Usually in quantum mechanics, we wouldn't consider this to be a good state that a single particle could be in that kind of state for a psi of x at time t equals 0, because it's not normalizable. So probably that vector wouldn't, we would say our vector space is such that that's not one of the vectors, right? We're considering, for the most part, normalizable states. How does that differ from g of x, which just has an absolute value there? Well, that one is not badly behaved, right? Because you have to do this integral, but this is not divergent. That's 2 times the integral from 0 to infinity, because this is an even function. So now I can write that as 2 times the integral from 0 to infinity of e to the minus 2x. And then I don't need the absolute values anymore because x is always positive where we're integrating. And so that is e to the minus 2x over minus 2 evaluated between 0 and infinity. Upper limit is 0, and the lower limit gives a 1/2 with the extra minus sign that goes with the lower limit. 1/2 cancels the 2, and so it looks like this thing under the integral is 1, under the square root is 1. When we take the square root of 1, we get 1. So I wasn't expecting that, but because I didn't look at the end of my solution before I wrote it down. But it turns out that nice simple function is normalized, amazingly enough. So say that again. It goes away because the upper limit gives 0, e to the minus infinity, that goes to 0. And the lower limit gets an extra, you subtract off the lower limit. So the minus sign from subtracting kills off that minus sign and then gives a plus. All right, good. Just practicing with mechanics, easy enough. Each one of these steps is easy. It's just that, you put enough pieces together, and we're going to put, we'll do like double this number of pieces. It just begins to, you've got to know what mode to go in when you're trying to calculate the norm of something or take the inner product or create something that's orthogonal. So that's norms. And I need to keep looking at my notes here to make sure I'm not forgetting anything, but I think we're not. Okay. Now, within a vector space, there's always an infinite number of vectors in a vector space, even a 3-dimensional vector space, right? We've got infinite number of vectors that point everywhere. We're talking about infinite dimensional vector spaces. They certainly have infinite collection of vectors. We now want to talk about subsets of the vector space. Could I take a collection, a special collection of vectors that's not the complete vector space, that has this special property, so that if you choose any arbitrary vector in the vector space, I could write it as a linear combination of the vectors in this collection that I've named, right? The subset of the vector space, okay? And if my subset is infinite, right, then we're talking about an infinite linear combination in the sense that we were talking about in chapter 2, okay? So this, what we mean by linear combination kind of depends whether our collection of vectors that we're talking about, which we're hoping is going to be complete, is discrete or continuous, right? So I might say, let me just write some things on the board here. I'll unshare for a second just to make sure it makes it in the video. I might say my vector space is going to be the one we've called capital 2 minus infinity to infinity. That means the set of all square integrable functions on minus infinity to infinity. So in other words, they're normalizable functions. That's what we're usually concerned with when we're representing a state of a function, a state of a particle by a function of x. In that, there are lots of different states in there, like a Gaussian function or something might be one of them, right? Or, you know, some other function that's 0 and then it goes up to 1, that goes back down to 0. Those are all different vectors that are square integrable. They're elements of that vector space. I could take a subset of those, which are just the solutions to the time-independent Schrodinger equation for the simple harmonic oscillator that we talked about, you know, in section 2.4 or whatever it was. Remember, we have an infinite collection of them, right? So there's a discrete infinite collection of them. That certainly is a very small subset of this. I mean, it's an infinite collection of vectors, but there are lots of ones that are nothing like the solution to the simple harmonic oscillator. Solution to the time-independent Schrodinger equation for the simple harmonic oscillator. And we said, no matter what psi, capital psi, as a function of x, which would be an element of that, the claim is no matter what one you choose, you can write it as an infinite linear combination of these. And that's saying, so one thing we could say about that is that's telling me that this collection of functions, this infinite collection of functions, even though it's a small subset of the vector space, is complete. It's not missing any pieces. If it were missing a piece, then we wouldn't be able to write an arbitrary function as a linear combination of it. So going back to your more familiar kind of vector spaces, you might say in R3. That's our good old three-dimensional vector space from physics 210 or whatever. I might say, here's my collection, and I'm going to ask whether it's complete or not. X, suppose I told you what X, Y, and Z axes are. X hat plus Y hat is a second vector, and let's just end there. So we're in a three-dimensional vector space, and I've given you those two vectors. Can I write any vector in a three-dimensional vector space pointing to somewhere in the X, Y, Z axes as a linear combination of these two? No, of course you need a basis that consists of at least 3, right? So the simplest case, the one we always use without thinking is that, well, this is a complete set for vectors in 3 dimensions. That's a complete set. They don't always have to be orthogonal to each other. Certainly this would suffice. X hat plus Y hat plus Z hat. You'd have to think hard to how to write an arbitrary vector as a sum of those, but you probably could work out the algebra and figure out what the coefficients you needed All that really matters is that these vectors are linearly independent of each other. Right? I could say, let's take a vector that points this way and one that points this way and that one that points down that way. As long as no one of them can be expressed as a multiple of the other two, you're good. Now, for a complete set, I could also have extra stuff in there. Maybe I'll throw in a z hat and a z hat minus x hat. Now you might say, well, you've got too many things in that collection. It's still not the whole space. There's an infinite number of vectors in 3 dimensions. Here, I've only taken a collection of 5. I would still say it's complete because it's possible for me to write any vector as a linear combination of these. In fact, I could write it many different ways. I really only needed the first 3, maybe. Still complete. Complete means you've got enough to express everything as a linear combination. Maybe you got too much. That's not a problem for complete, but you want to make sure you have enough. Okay. So let's go back to the slides and see what I've got on here. Okay, so for a discrete collection, what that means is I should be able to write it as an infinite linear combination with an infinite sum, different coefficients out in front. There should be some collection of coefficients that for which it makes it true for an arbitrary W there. And if I've got a continuous collection of vectors, so maybe I could say, oh, you know, I solved for the free particle potential energy, which is just V equals 0 everywhere. We didn't get a discrete collection of these. We got one for every real k. You know, maybe I could write the collection as k is between minus infinity to infinity. That's a continuous collection of vectors, right? And in that case, it's still not all the vectors in this vector space. There are other ones that are not of this form. These just happen to be the ones that are e to the I kx kind of function. There are lots of other functions. The claim is you take any square integrable function and psi of x and 0, doesn't matter what shape it has, you should be able to write it as an integral sum over all of these functions, psi k, with some coefficients out in front, summed over all k. That's the analogous kind of situation. That's how it would be written in terms of functions. Here I've written it in terms of abstract vectors, but same idea, right? Abstract vectors there. Okay, and those are examples where, well, there's just enough of these functions. We don't have too many. I didn't throw in any extras. You need all of them if you're going to write them all. There's no excess there. But it's okay for completeness to actually have some extra in there. Let me, same idea there. Okay, I think we're supposed to do, my worksheets are kind of jumbled here, but we're now supposed to do on the second worksheet that has a backside, problem number 7. Oh, I see. And I also missed 4, 5, and 6 on this one. 4, 5, and 6 have to do with the norm. So why don't we, I want you guys to have a lot of practice with just working with this notation. So try on the 2-sided worksheet 4, 5, 6, and then 7. 4, 5, and 6 have to do with inner products and norms, and 7 has to do with complete collections. I'll put some answers up on the board so that if you want to check your work for these, and then if you're not matching me, you could ask your neighbor, and then you can ask me. I guess 5B we already did on the other worksheet. That one's a repeat, so make sure you can do the work yourself. Just noticed with our new clock that we have 5 minutes left. Is anybody having trouble with 4? Maybe I could come by individually and help rather than stopping to go as a group here.
So just multiplying the two, like it is.
Yeah, so we're not multiplying the sets together like that, but we take, just like if you have 2 vectors in 3 dimensions, right? I have an AX, AY, AZ components, right? And BX, BY, BZ components, right? Multiply together the X components and then add that to the product of the Y components and the product of the Z component. It's the same thing here. So these are the components. So you shouldn't have that little squirrely brace there, but you are going to sum all of them together. And what you're summing is the star of the first component times the second component. And then you're correctly combining those together into a single kind of fraction with a power in it. So in this case, the first one's component, if we're doing WV, this one, W1 gets a star, but the star just changes the I to a minus I. What happened to my, I don't know what happened to my I there? I must have misread that as a 1, but it's an I. So this should have a minus I actually in front of it. Yeah, you don't need the brackets, and then it's a geometric series is what you need to realize. Are other people agreeing that I guess when I was looking at this, I misread the I as a 1 or something, but somehow I didn't put the I in there. In any case, it's the first one in the inner product, so the I gets turned into a minus I, and then it gets factored out in front of the sum, and the sum itself, when you factor out the minus I, is 6/5. Anybody want to talk more about that? That's a geometric series, which is kind of the only one I remember. Okay, so in this case, when we calculate the inner product, we're going from 0 to infinity in this way of labeling, right? All these go from 0 to infinity. The first one in the inner product has the I, and so it gets changed to a minus I, and I'm just going to factor that out in front of the sum. And then we have a 1/2 to the n times a 1/3 to the n. Right, so we're saying just like in 3 dimensions, right? If you have an AX, AY, AZ components, BX, BY, BZ components, you multiply the X components together and add that to the product of the Y components, add that to the product of the Z components. Here, I do the product of the 0 components plus the product of the 1 components, plus the product of the 2 components, plus the product of the 3 components. And so that is this infinite series here. So let's do the step before that. This was, we're supposed to calculate the inner product of W with V. And what that means is whichever one is the first one in the inner product, that's the one that gets the star here. So my W components have an I over 3 to the N. And so I should take the star of that, minus I over 3 to the N. And the second one doesn't get conjugated. It's real anyway, so it wouldn't have mattered. And then I'm saying when I have an infinite sum, anything that's just a pure constant, doesn't have any n dependence, I can always factor out in front of the infinite series. And then what's left can be combined as a 1 over 6 to the n. And that's a geometric series with that's written in the upper left-hand corner with capital X equals 1/6. 1 minus 1/6 is 5/6 in the denominator, which is 6/5 when you take its reciprocal. So the minus I just comes along for the ride. I've got to change my solution on that one. I forgot that I business there. And any last questions on this? Why don't you guys try to finish those up? I'm hoping you can do at least 4, 5, and 6 either in short order or you'll be confused about them. We can talk about them at the beginning of tomorrow when we meet over in 023, the electronics lab. And then we can go through problem 7 a little bit more carefully because it's about the new concept of a complete collection of vectors, which is a subset of the vector space. Any last things you guys want to talk about on this worksheet before we end? All right. So we'll meet down the hall tomorrow like we did before. First hour, we'll be continuing this talk. Second hour, we'll just break and do MATLAB. And wherever you're at on that, feel free to do it. If you're done, just show me what you've done, and that's great. And you can start working on the homework wherever you are on the homework and use that time to do that. Sure, I do. So we're going to talk about some of the homework problems that were due Monday, but you should for sure turn them in today.